please explain Hawking radiation and how will a black hole vanish after trillion, etc. years. So Hawking radiation is a very interesting effect. So what we know about black holes is this. A black hole is essentially an object whose that is so massive and so compact and so dense that even light cannot escape from it. Not even light can escape from it, which means that it can absorb mass and energy. What this indicates is that an object from which nothing escapes, but an object which will swallow or eat up or absorb mass and energy, which means that an object like this should only be capable of growing larger. It should never be something that can decrease in size. That is our understanding of black holes. That's what general relativity tells us. Now, what Stephen Hawking found, I think he had visited the Soviet Union, and a couple of Soviet scientists told him that black holes, especially rotating black holes, should be capable of emitting radiation. So Stephen Hawking applied quantum field theory to the edge of black holes, to the space-time that is around the event horizon of black holes. And what he found was that black holes do emit radiation. So here's one way of looking at it. Let's say I have a black hole, okay, a spherical object, and let's say this is the event horizon here, and the black hole center is here. Now we know from quantum field theory says that the entire vacuum of the universe is made up of fields of various kinds, and there is this vacuum energy in there. So the vacuum of space is teeming with these virtual particles. Particle-antiparticle pairs are constantly being created and annihilated in accordance with Heisenberg's uncertainty principle. So this particle-antiparticle pair appears and annihilates very, very, very quickly, very rapidly. So quickly that it does not violate the time component of Heisenberg's uncertainty principle. So the entire vacuum of space is actually teeming with these particle-antiparticle pairs, and we have experimental confirmation of this Casimir effect. So what we know is that you have this in empty space. Now at the edge of a black hole, at the edge of the event horizon, let's say a particle-antiparticle pair is formed. Now the energy is borrowed from space-time itself, and when they annihilate each other, the energy is given back to space-time. So the net change in energy is zero. Let's say a particle-antiparticle pair is formed right outside the event horizon of a black hole, and it goes into different directions, and before it can recombine, one of the particles or antiparticle is absorbed by the black hole because it crosses the event horizon, and the other one is then free to go away, which means that from a virtual particle it became a real particle, right? Now the energy was borrowed from space, from space-time, from the vacuum of space. It was supposed to be given back to the vacuum of space. Now what happened is that one particle went inside the black hole, and the other particle is now available to us. So we have gained the energy of this particle, which effectively means that to compensate for this energy we gained in violation of Heisenberg's uncertainty principle, it means that the particle that went inside the black hole has negative energy or mass, which means the black hole actually shrinks by a little bit when this happens. And that is the process. That is one way of looking at Hawking radiation. The actual manner is different. This is a good analogy of how this thing happens. So because of the creation and annihilation of particles in space-time, when it happens at the edge of the event horizon of a black hole, you have these particles that escape from it, and which we see as a flux of energy and radiation actually. And what goes inside the black hole has negative mass. So over time, the black hole slowly over time shrinks. So for somebody who is standing or sitting far away and observing a black hole, it looks like the black hole is radiating energy. It is radiating particles. It is radiating. It is emitting radiation. And it is this radiation that's called Hawking radiation. This is called black body radiation. Okay, that is a term that you can look up. So an object like a black hole actually emits radiation. And we know that anything that emits radiation has a temperature. So black holes have temperature. The larger a black hole, the colder it is. The smaller a black hole, the more radiative it is and the hotter it is. So the thing is, the smaller a black hole, the more radiation it emits, and the faster it emits radiation, and the hotter it is. And therefore, it gets smaller quicker. So small black holes shrink faster and faster until at the very end it explodes in a burst of Hawking radiation. So that is Hawking radiation. That's what it is. Black holes, even though they are dark, even though they are black, they still do emit Hawking radiation by this semi-classical theory of Stephen Hawking. Have you ever observed Hawking radiation? Thus far, we don't have any real evidence of it. But theoretically, this is what happens. So that is the answer to your question. So how long will a black hole last? Large black holes, they have lifetimes that exceed the current age of the universe. So they could be around forever. And they are so cold that instead of emitting radiation, they absorb the cosmic microwave background radiation, and then they grow larger. So black holes beyond a certain size, they are most likely essentially immortal black holes. They will live as long as the universe exists. Smaller black holes have a finite lifetime. They emit radiation. And so you can calculate what exactly the temperature and the lifetime of a black hole is. There's a formula for that. So certain black holes are de facto immortal, and some smaller black holes will eventually meet their fiery, explosive demise. So that, sir, in brief, is what Hawking radiation is.